Let's look at 2.4. We're going to start talking about arc length of a curve as well as surface area of a revolution. So if I were revolving that curve. So we're going to first start off by estimation, and then we're going to find the exact length. We're going to estimate the length of a curve by breaking it up into smaller segments, and then estimating that curve as if it were a straight line and find the length of that straight line. Then we're going to add those all up to find the length of the whole curve. So our goal is, if you have some function, like you see in this picture, that's got some kind of curve to it, we're going to try to find the length of that curve. So what we're going to do is going to first break it up into these smaller segments. So these bunch of smaller pieces right here, and each one of those segments, we're going to connect with a straight line, because straight lines are a lot easier to calculate the length of. And they're going to find the length of those straight lines. So let's start off with just that first one. We're going to find the length of that straight line. And the best way to find the length of a straight line is to visualize that as a triangle. So I'm going to zoom in a little bit so we can see that. I'm going to look at this as if it were a triangle. And if I think of that as the right triangle that I see right here, it looks like the bottom of that triangle is a distance in the x direction. So that is a change in x. That's that bottom leg of that right triangle. And then the side leg of that right triangle is a distance in the y direction. So that would be my change in y. So that's going to be the triangle that I have, and I'm looking for that length L right there. That's what I'm really looking for, is the hypotenuse of that triangle. And then what do we know about Pythagorean theorem? We know that a squared plus b squared equals c squared is the general Pythagorean theorem, where c is the hypotenuse of the triangle, which means if I wanted to figure out what the hypotenuse of the triangle is, I could take the square root of both sides. And we are going to be talking about positive, not negative, because I'm dealing with the length, or the hypotenuse of that triangle. So I'm going to use L for length, and it's going to become the square root of the delta x squared plus the delta y squared, because those were the two legs of the triangle. And then I'm going to simplify from there. What I'm going to do is a fancy version of factoring. All right, this is the part that's going to get really cool. So let me kind of go off to the side here, maybe even in a different color, and try to visualize some kind of cool factoring. So you don't need to write this down, just watch this part. If I were to ask you, not even in calculus, but let's just say in like an algebra class, to factor the expression 2x squared plus 3x, it'd be pretty obvious. You can just take out the x because there's an x in common, and I would be left over with the 2x plus 3. Totally valid. That is true. The point is it can be trickier. So if I were to think about, let's just say, the expression 3x minus 5, I could also factor that. Even though it doesn't feel like I could factor out a 3, even though it doesn't feel like there's a 3 in common. There's always a way of factoring. Factoring is really just a fancy word for divide. So if I were to divide the expression by 3, I would end up with x minus 5/3. And you can even double check that if you want by distributing after you've done the factoring to see if you end up right back to where you got. So you can, in fact, factor. And let me go back to this length here that we're finding to try to do a fancy version of factoring underneath that square root. So I'm actually going to factor out a delta x squared. I'm going to leave that square root alone for right now. I'm going to keep it there. I'm starting to erase it. I'm just going to ignore it for right now, but I'll come back to it later. And then after I have factored out the delta x squared, this guy is left over with 1 plus, and just like I showed before, factoring was a fancy way of dividing, so that would become delta y squared divided by delta x squared. That was me having factored out the delta x squared underneath the square root. Okay, now I'm going to continue with this simplification. And now that I have that, the product underneath the square root allows me to take the square root of each one separately. So the square root of delta x squared is just delta x. And then I'm left over with 1 plus delta y squared over delta x squared. And then a lot of times you're going to see people rewriting that as the square root written first, the delta y over delta x squared, and then the delta x on the other side. That doesn't technically matter. It's a product, so it doesn't matter. And remember, all that, though, was to find the length of just one of these little pieces right here. Right? That's really what it is. And then we wanted to add up all of them. Right? And then not only did I want to add them all up, I wanted that estimate. This is just an estimate. So I can add up all of those. So my actual length, I should probably throw in some kind of sigma notation in here. I'm not going to right now though, because we're now going to skip straight to the fundamental theorem of calculus. I don't need to add up all infinitely many. There should be infinitely many because I should have broken it up into even smaller and smaller pieces. But adding up infinitely many was the integral. And we also are thinking as these are getting smaller and smaller, we're taking the limit, right? We're taking the limit as delta x goes to 0. This should get shrink smaller and smaller and smaller. And maybe from Calc 1, you remember that delta x was often called an h, and the limit as h goes to 0 of the change in y over the change in x really was the derivative. That's kind of where that dy over dx notation came from. So after all that work, my final total length could actually come add up infinitely many. So instead of doing the sigma notation, we get to do that integral of the square root of 1 plus the derivative squared dx. Okay, that was after I've taken the limit as h goes to 0. That's where the derivative notation came from, and adding up infinitely many, that's where the integral came from. So that's the general idea. That's sort of my hand wavy proof of this theorem for arc length. So if f of x is a smooth function over this interval from a to b, then the arc length of the portion of the graph only from a to b, where a and b are x values. Okay, so that f of a and f of b were the y values. B is the integral from a to b of the square root of 1 plus the derivative squared dx. All right, so now we have the formula, then that's just going to be a plug and chug. So let's do an example. Set up an integral that's going to find the arc length of this curve. I'm going to graph it. So this one, I didn't ask for the graph, but just like we've been doing so far in this unit is when in doubt, graph it to try to visualize what you're finding here. My graph is f of x equals sine of x. So here is my f of x equals sine of x. And I'm only going to care about this from 0 to pi over 4. So it's just this little piece right here. Maybe it's not perfectly to scale, but that's what we're trying to find the length of. And what do we know? We know the length is the integral from a to b of the square root of 1 plus f prime of x squared. So the integral from 0 to pi over 4 of the square root of 1 plus the derivative squared dx. So maybe you know the derivative off the top of your head. Maybe you're going to need to use some simplification rules that you've learned in Calc 1. Perhaps you will need a product or a quotient or a chain or any kind of rules. I don't know. In this case, it was easy. The derivative of sine is cosine. So that's where that cosine comes from. So the answer to this question is the integral from 0 to pi over 4 of the square root of 1 plus cosine squared of x dx. It only asked me to set up the integral. It did not ask me to solve. Ta-da. Okay, let's do another example. Same kind of idea. Here's another function. I'm going to do this one without drawing the graph, although you certainly can draw the graph. It's really helpful to visualize it. Let f of x equals 2x to the power of 3/2. Find the arc length over the interval from 0 to 1. So I know in that formula that I'm going to eventually need a derivative. So I like to start off with the derivative right away because I know I'm going to need that. So the derivative, 2 is a constant multiple. I can bring the 3/2 down and subtract 1 from the power. That was the power rule. I ended up with 3 times x to the 1/2. Okay, so then my arc length is going to be the integral from a to b of the square root of 1 plus the derivative squared dx. And then make sure you simplify. This one I actually need to integrate because it asked me to find and calculate that arc length. So it's going to be the square root of 1 plus 3 squared is 9, and x to the 1/2 squared is just x. And then here's where I can go through and do that integration. Before I do the antiderivative, I'm going to rewrite it as, instead of a square root, a power of 1/2. Only because I think that's a little bit more visual for those of us who are trying to think about u sub. You could go ahead and do the work to let your u be that inside part. Let u be 1 plus 9x. Your u sub will work beautifully. Or because the inside is linear, maybe you remember that, I can skip the work for u sub. So I'm going to skip the work for u sub. The inside is linear, so I can just simply add 1 to the power, divide by the new power. so long as I also divide by the constant multiple of the inside part. You had to divide by that as well. And I don't need a plus C because I have bounds. I am going to need to simplify that though a little bit. So that's going to become a 2 over 27 times 1 plus 9x to the 3/2 evaluated from 0 to 1. This is because, by the way, this is because 3 times 9 is 27. And 27 divided by 2 is on the bottom. So to divide by fractions, you multiply by the reciprocal. Okay, and then I'm going to plug and chug. So now I have 2 over 27. If I plugged in 1, I got 1 plus 9, which is 10 to the 3/2. Minus 2 over 27. If I plugged in 0, I got 1 to the power of 3/2, and 1 to the 3/2 is just 1. So I don't need to write it. Ta-da. Ta-da. And this one is not an area. It's not a volume. It's just a length. So it's just units. Like if I were to give you units, maybe this were measured in feet, then it would be whatever that number is, feet. Not feet squared, not feet cubed, because we found a length, not an area, not a volume. All right, let's do another one. Same kind of idea. So let's find, so this next example, find the arc length of the curve. X equals 2y minus 4 for y going from -3 to 4. Now it's the same idea, only instead of written as a y equals, it's written as an x equals. I could draw the picture if you'd like. Everything is now just sort of tilted on its side, but everything is exactly the same. So the length is now going to be, I'm going to rewrite this formula. I recommend you write this new one down as well. It's now going to be the integral. I'm going to not use letters A and B. I'll use from C to D of the square root of 1 plus, but now it's g prime of y squared dy, because everything was tilted on its side. And if I were to find that, you can think of that original function. It's not a function in this case, but it is an expression. You can think of it as g of y is equal to 2y minus 4. It's a function of y, I guess, right? And that would mean that g prime of y in this case is just 2. So then my integral becomes the integral from -3 to 4 of the square root of 1 plus 2 squared dy, which becomes the integral from -3 to 4 of the square root of 5 dy, and the square root of 5 is just a number. So the antiderivative of a number dy is just that number times y evaluated from -3 to 4. So the square root of 5 times 4 minus the square root of 5 times -3, which is a total of 7 square root of 5. Ta-da. Okay, let's practice another one. We're on a roll. This one's a little bit trickier. Okay, so make sure you follow along. You're going to want to show all your work for this one. It will definitely require some work. Oh, sorry about that. I didn't mean to scroll past it. There we go. It's definitely going to require a lot of space. Okay, I'm warning you for this one. We can do it. So find the arc length of this guy. And what I'm going to ask you to do is give the answer as a simplified exact value. So I don't want any decimals, and I want to see all the work for the integration. The integration is kind of tricky for this one. Okay, so I know I'm going to need a derivative, right? That formula required a derivative. So let's find the derivative here. Before I find the derivative, I'm just going to write the function so I don't forget it. It's 1/3 x cubed plus 1/4 x to the -1. I know an x on the bottom is the same thing as an x to the -1. More visual for me to be able to use the power rule when I take the derivative. So the derivative, I bring that 3 down, subtract 1 from the power, bring that -1 down, and subtract 1 from the power. I also know I'm going to need, I haven't even done the integral yet, but I know I'm going to need to square that derivative. So this one has a lot of ugly algebra, so I'm going to just show all of the work for that. And to write something squared, to have a binomial, that means there's 2 terms squared, I have to write it out twice and distribute or FOIL. Okay, so I'm going to actually start to do that foiling. This guy times that guy, x squared times x squared is x to the 4th. And then this guy times this guy. So x squared times -1/4 x to the -2. X squared times x to the -2, those cancel and become 1 times the -1/4. So I really did just get a -1/4. And then I got to do my inside. So -1/4 x to the -2 times x to the positive 2. Those x's will cancel, and I just got -1/4. And then my last -1/4 x squared times sorry, I said that wrong. -1/4 x to the -2 times -1/4 x to the -2. Those two negatives became a positive, and I got 1/16. And then I add the exponents. So -2 plus -2 really is -4. And then that simplifies to be x to the 4th minus 1/2 plus 1/16 x to the -4. Lots of algebra. We can do it. Now, going back to that integral formula, I'm going to write it down over here that I need. I'm trying to find the arc length. It's the integral from a to b of the square root of 1 plus the derivative squared dx. Now, I have the derivative squared. I might as well do the +1. I'm doing it one piece at a time. So let's go ahead and do that +1. So 1 plus my f prime of x squared is 1 plus x to the 4th minus 1/2 plus 1/16 x to the -4. And then some things combine. The 1 and -1/2 simplify, and that becomes x to the 4th plus 1/2 plus 1/16 x to the -4. Okay, really great. Pause for a second and pause what you're writing and just watch with me for a second, because this one's going to be a little bit trickier. So just pause what you're writing down and keep playing the video and just watch with me. What I have so far is 1 plus f prime squared is equal to x to the 4th plus 1/2 plus 1/16 x to the -4. I want to point out how similar this looks to when I had just squared or FOILed the binomial in the step before. Take a look at those two boxed things. Those look very similar. The only difference between f prime squared and 1 plus f prime squared is the first one has a -1/2 and the second one has a +1/2. Okay, that's the only difference between those two. So x to the 4th minus 1/2 plus 1/16 x to the -4 is equal to this binomial squared. And that binomial had a -1/4. I have the exact same thing, but a +1/2. So it will also come from that same binomial squared, but with a positive. So that's what it is going to become. This is going to become x squared plus 1/4 x to the -2 squared. I kind of factored it by noticing a pattern. I'm going to point it out one more time. When that binomial had a negative and then I FOILed it, I had a -1/2. So if I have a +1/2, it would come back from a binomial squared, but with a positive. And you should check your work. You can easily check your work. If I were to take that last thing that I have written down there on the bottom and actually FOIL it out, you would end up with x to the 4th plus 1/2 plus 1/16 x to the -4. Okay, all that to say, this is then going to become the integral from 1 to 2 of the square root of x squared plus 1/4 x to the -2 squared. 1 plus f prime squared turned into this binomial squared. All right, now it becomes really easy. So if you need to pause and rework that algebra, feel free to. But now we're going to go through and we're just going to pick up our pencil and just do the calculus. Now the calculus is pretty easy. So that's going to become the integral from 1 to 2, the square root and the squared go away. It's simplified quite nicely. Now I can just take the square integral of each one, and the antiderivative, I can add 1 to the power, divide by the new power. For each one of those, my bounds were from 1 to 2. I'll plug in some numbers. If I plugged in 2, I got 8/3 minus 1/8. I'm going to point out where that 1/8 came from for a second, so just watch if you can. When I plugged 2 into here, what did I end up with? 1/4 times the -1 was the -1/4. And then 2 to the -1 is 1/2. So I had a 1/4 times the 1/2, which is where the 1/8 came from. Okay, minus, now I'll plug in 1. I got 1/3 minus 1/4 because that positive and negative did turn into that negative. Okay, and then feel free to use your calculator. Make sure you use that math fraction so you can end up with an exact answer. So I would type that into my calculator like this, having distributed that negative, and then make sure you type it in. But remember, before you click enter, click the math, select the fraction button, and then click enter. You might have to click enter twice. I can never remember. But either way, once I did that in my calculator, I ended up with 59/24. Ta-da! A little bit trickier, a little bit trickier. All right, that's our arc length. It's one formula. So the formula is not so bad. The arc length is always going to be just that one formula, ta-da. It's a matter of doing the calculus and maybe the algebra that could be a little bit trickier. All right, that's the arc length. There was a second half of this section, which is going to be a surface area instead of an arc length. So let's take that function, and instead of find the length, let's revolve it around the x-axis. And as I revolve it, you see how each little piece created its own little circle. And I want to find the surface area when I add up all of those, right? So I want to find the circumference of each of those circles and then add them all up, hence the integration. So let's think about the circumference of a circle. Hopefully we remember it's 2 pi r is the circumference of a circle. But I'm also going to want to multiply that by its length, because if I think about this little tiny segment right here, there's a little length to it, right? There's a width to it, like that delta x, like we were doing before. So times the length of it. So that would mean that my surface area, we're going to add all of them up. I'm going to have a 2, a pi, a radius, and the length, which we already have a formula for. Okay, so that's where this formula is coming from in that theorem. Let's look at that theorem that we've got typed here. Here's the surface area. If f of x is a non-negative smooth function over the interval from a to b, then the surface area of the surface of revolution formed by revolving the graph of f of x around the x-axis is given by surface area is equal to the integral from a to b of 2 pi times my function times the square root of 1 plus f prime squared dx. Let's write some stuff down. 2 pi, the radius, and then the length. Look back at that circle that we did the revolving for. Notice the radius is the actual function. So that's why my radius was f of x. Okay, so now we have the formula, and it would be the exact same thing if you were revolving this around the y-axis, although if that were the case, then you would have a dy. All right, so now I have our two different formulas for the surface area of revolution. Let's practice. Not only are we going to practice, I do want to show you a quick visual of it. Let's imagine that I have some curve that you see there in 2 dimensions on the left. This happens to be a 2 times the square root of x. What I'm going to do is I'm going to pick it up and revolve just the line, just the curve around the x-axis. And you should see this is like a hollow object. This is what I'm finding the surface area of. Okay, that's the visual for us. Let's do the practice. Find the surface area generated when the graph of f of x equals 2 square root of x. Here is my f of x equals 2 square root of x on the interval from 1 to 3. Here's my 1 to 3 is revolved around the x-axis. So when I revolve that around the x-axis, you're going to end up with some hollow object that this is what I'm trying to find the surface area of. Think of it as hollow. I'm not filling it in. I'm not finding a volume. We're just finding the surface area. Okay, all right, so luckily we have a formula. Surface area is going to be the integral from a to b of 2 pi times the function times the square root of 1 plus the derivative squared dx. And perhaps you know the derivative off the top of your head. Maybe you need to do a little bit of work. 2 is a constant multiple. The derivative of the square root is 1 over 2 square root. So the 2's cancel, and I end up with 1 over the square root of x as the derivative. Then we simplify. So I have the integral from 1 to 3 of 4 pi times the square root of x times the square root of 1 plus 1 over x dx. And then we simplify. 4 pi is a constant multiple. It can come on the outside of the integral. When you have a square root times a square root, you can put them both underneath the same square root, and then I'll be able to distribute accordingly. 4x times the integral from 1 to 3 of the square root. Once I distribute this x across, x times 1, ooh, I don't know where I changed the color, sorry, is just x plus, and then x times 1 over x is just 1. And then this becomes the integral from 1 to 3 of x plus 1 to the power of 1/2. You should notice that my inside is linear, so I can skip the u sub part and just do that calculation. So this will become 4 pi times, I add 1 to the power, divide by the new power, so long as I also divide by the constant multiple, and my constant multiple was 1 times x. And then I'm going to evaluate that, it looks like from 1 to 3. So this is 8 pi thirds. Hopefully you can see where that's coming from, times x plus 1 to the 3/2 evaluated from 1 to 3. I just multiplied by 2/3 because that's how you divide fractions, is you multiply by the reciprocal. And then I'll plug in some numbers. I'm almost here. If I plugged in 3, I would end up with 8 pi thirds times 4 to the 3/2 minus 8 pi thirds times 2 to the 3/2, which you can simplify. I'm almost out of space. We are going to do that extra example, but I'll simplify this. 4 to the power of 3/2 is 8. Feel free to use your calculator if you need. And so then this would end up with a 64 pi thirds minus 8 pi thirds times 2 to the power of 3/2. Ta-da! This is units squared because we found an area. It was a surface area. It wasn't a length. It wasn't a volume. It was an area. Whoo-wee. All right, let's do another one. Let's do another example. Find the surface area of the surface generated when the graph of y equals, it looks like in this case, 3x quantity to the power of 1/3, where x goes from 0 to 8/3. But now I'm revolving around the y-axis. So anytime you're doing a surface area revolved around a y-axis, you really want to do the dy. You don't even need to draw a picture. Surface area. That's not the same for the washer shell method, right? The washer shell method volumes, you had to draw a picture. You had to. Not so much for the surface area. You really don't. You can. It's helpful. So I need to do a dy. So I need to get x by itself. So this becomes y cubed equals 3x. So x equals 1/3 y cubed. You might call that g of y instead of an x equals. That's fine, because then you can do my g prime of y is y squared. Then I have everything I need. I plug it into the formula. Surface area is the integral from c to d of 2 pi times my function times the square root of 1 plus the derivative squared dy. My function was 1/3 y cubed because I am doing a dy, and my bounds need to be y values. So my bounds are from 0 to 2. Take a second. Think about it. X equals 0 gave me y equals 0. And then x equals 8/3. 3 times 8/3 is just 8. And then 8 to the 1/3 is 2. Okay, then we integrate. So I have a uh, 2 pi 3, the integral from 0 to 2 of y cubed times the square root of 1 plus y to the fourth dy. The inside right here is not linear, so I cannot skip any steps. I got to show my work. I'm going to let you be 1 plus y to the fourth. Du is 4y cubed dy, so du divided by 4 is y cubed dy. Then I can simplify the integral. I'm going to highlight that so you can see it. The y cubed and the dy turned into my du over 4. I am going to need to change my bounds because I changed my variable. You should always change your bounds when you change your variable. So if I plugged in 0, my u became 1 plus 0 to the fourth, which is 1. And if I plugged in 2, my u became 1 plus 2 to the fourth, which is 17. That's where those bounds come from. And then I'm going to simplify a little farther. This is going to become a 2 pi over 12, the integral from 1 to 17th of u to the 1/2 du. I just did the 3 times 4 on the bottom. And then I'll simplify that to be pi over 6. Add 1 to the power, divide by the new power. And you know that dividing by a fraction is multiplying by its reciprocal. And then this can become a 2 pi over 18, which is the same thing as pi over 9. Sorry about that. I wrote that a little strange there. Okay, times 17 to the power of 3/2 minus pi over 9 times 1 to the power of 3/2. So pi times 17 to the power of 3/2 over 9 minus pi over 9 is correct. Or if you want, you can write that as 17 times the square root of 17 pi over 9 minus pi over 9. Ta-da! All right, so now we have everything we need for arc length and surface area of revolution.